So here we're going to continue our work on rate of change. In this lesson we are studying instantaneous rate of change. So we'll talk about what that means in a second. The first thing I want to do though is just clarify some definitions here. These are probably familiar to you already. These come from physics. So if you've had physics or you're taking physics right now, these are definitely going to be familiar. The definitions are just position and velocity. So position is an object's distance from a fixed point of reference. So in our Usain Bolt example from the last lesson, we might be talking about distance from the starting line, right? Or you're taking a trip, it could be distance from home. In a lot of calculus problems, we just say distance from the origin. But distance doesn't make any sense without saying distance from something, right? So position is an object's distance from a fixed point of reference. And then velocity, you know, is somewhat synonymous with speed, right? Velocity is, for our purposes, just the rate of change of position. So it's how fast you're going, right? So the speedometer on your car, you can think of as essentially a measure of velocity. The important thing to note is velocity can be positive or negative, right? So positive velocity means we're going forwards or away from our fixed point of reference. Negative velocity would mean we're going backwards. So velocity has a sign. Your speedometer in your car doesn't have a sign, but you can imagine if it said negative numbers when you're going in reverse, that would be a good example of velocity. By the way, velocity we often write as v of t in our function notation, and then position we write it for some reason as s of t. Okay, so that's what I call it down here. So distance traveled in this particular graph is position. We want to estimate the velocity at 9 seconds. Before we get into that, I'm going to start by asking you to find just the average rate of change over this entire interval, from 0 to 10. So here are those 2 points, 0, 0, and then 10, 100, right? So my average rate of change just looks like this. You're probably very good at this by now if you're watching this video. And we get 10, and then we have y's per x, right? So meters per second in this case is my average rate of change. Okay. So that's what we did in the previous lesson. This is not asking you for that anymore. This is asking you to estimate the velocity at 9 seconds. So that point, we have 9 here. That point's up here, right? So what you should not have said is something like 95, because that would be position at 9 seconds. We want the velocity at 9 seconds. So we write this down as v of 9. And what this is really asking you is, this is a graph of where your car was at. We want to guess at what the speedometer says at this particular point. So another way of rephrasing that is, we want the rate of change, rate of change of s at t equals 9. And we just want to make a guess. Okay? Well, one guess, maybe not a great guess, but one guess might be the rate of change we just found, right? So we know on average, from 0 to 10 seconds, we traveled at 10 meters per second. So one way we might guess is use the average rate of change of the whole function. And notice this isn't a great guess, right? Because we know from our previous lesson, by the way, this graph is really similar to our Usain Bolt graph, right? I just simplified the numbers a little bit. So we could think of this as Usain Bolt's 100-meter dash as well. Remember from that lesson, we determined that he had started out slow because the slope is not very steep, right? And then got faster and faster to a certain amount of time, and then he starts to tire out towards the finish, right? And the curve levels off. So the velocity at 9 seconds in this particular example, we're going pretty slow compared to the rest of the graph because it's in a flatter part of the curve, right? So to make these estimates, we don't necessarily need to use the whole graph. We could use a different average rate of change, right? So here, I ask you to just use the interval 8, 10. So that's from about here to here. I'll have you do that real quick. We'll see what you get. So here are my 2 points, right? And then our math looks like this. So 5 meters per second is our average rate of change from this interval 8 to 10. Remember, the point we're interested in is t equals 9, right? So we're looking for v of 9. We're trying to estimate v of 9. So here, our secant line, Notice if I draw that in, it looks a lot closer to the actual slope of the curve versus this one. It's not very close at all, right? So my guess, say v of 9, we'll use the squiggly equal sign to show that this is an estimate. We're not being very precise. 5 meters per second. This is a better estimate, right, than our previous estimate. We can see that visually because the slope of the line matches more closely the slope of the curve. Okay? So the size of this interval matters, and we can pick intervals that are smaller to get better estimates of what our speedometer says at a certain rate. So the smaller the interval is around a point, the better estimates we can make. We're zooming in on the point we're interested in. So here's our main idea. The main idea is that we can use our secant lines and average rate of change to estimate the rate of change at a certain point. And then the smaller we make that interval that we're looking at, the better the estimate is. This is super important. This is a great time to make sure you've captured everything on this first page of notes. So we'll move on now. This idea is quite powerful. So this idea that we're talking about now is instantaneous rate of change. So we want the slope now at one specific point. So v of 9 was what we're interested in. The way we can represent that is no longer a secant line, but we can draw a line that just touches the curve at that point. So the line is parallel to the curve at that specific point. That's called a tangent line. And the slope of that tangent line represents the slope of the curve. Okay, so we say, let's call this line L. We'd say L is tangent to S as our function at t equals 9. So we'd say it's tangent to the curve at a particular point. So what we're building towards is a method to figure out the slopes of these lines so that we can find this instantaneous rate of change exactly, and we no longer have to estimate. Okay, so let's look at a simpler example and see if we can't develop this method a little bit. So I have this function f of x squared, so this is just my plain old parabola. And we're going to make a bunch of secant lines to find the slope of a tangent line. So the question we're trying to answer here is, what's the slope of the tangent line at a specific point? And notice 2 shows up in every entry in the table here. So at x equals 2. So we're going to try to find the tangent line at that point, x equals 2. And I'm going to start by just sketching it. So I've used the straight line tool to make my life a little bit easier, but try to make it precise in your notes. So what we want, so you have a good example, what we want is for the line to just kind of bounce off this point 2, 4, and not cross the curve, but run parallel to that curve at that point. So try to make it look as much like mine as you can. Use a ruler or a straight edge if you got it. Okay? Now, what we're going to do is use secant lines and look for a pattern to see if we can't figure out what the slope of this line is. So it looks to me like the slope is probably 4, right? But we just drew it. We want to be precise, so we want to see what the pattern is to figure it out. So I've given you the first 2 now. I'm going to let you figure out the rest of the table. So here's what the rest of that table looks like. And notice my slopes tend to approach a certain number as my interval gets smaller and smaller. So here's an animation of what that looks like. So Q was our right-hand point, and then P is that point 2, 4 where we're looking for the tangent line. As Q gets closer to P, notice my red secant line starts to look a lot like that green tangent line. So if we want to find the slope of that tangent line, we can look for that pattern in the slopes of our secant line as we make Q very close to P. The slope of that tangent line, by the way, is 4, right? Because we see as we move down the table, my values are approaching 4. So here's the main idea, right? So if we're interested in finding this instantaneous rate of change at a point, we can see what the rate of change approaches on smaller and smaller intervals containing that point. This is big and profound.